Hello there, and welcome to the Sleep with Science channel. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps the channel to reach more curious minds like yours. Now let's begin. Close your eyes for just a moment, even as you listen. Somewhere above you, right now, beyond the ceiling, beyond the clouds, beyond the thin blue skin of our atmosphere, everything is turning. Not drifting, not floating still the way we imagine the vacuum of space to be. Turning, spinning, wheeling through the dark in slow, silent, endless circles. And here is the strange part, the part that has puzzled scientists for centuries. Nothing told it to do that. There was no hand that reached into the void and gave the first push. No engine, no motor, no divine finger flicking a planet like a coin. And yet spin is everywhere. It is in the seed of every galaxy, the heartbeat of every star, the quiet rhythm beneath your own 2 feet, because you, too, right now, in this very moment, are moving in a great circle around the axis of the Earth at nearly 1,000 miles an hour, and you feel none of it. Isn't that strange? Isn't that the kind of fact that makes you want to lie very still and just wonder? Because if you look closely enough, spinning isn't the exception in this universe. It is the rule. Moons circle planets. Planets circle stars. Stars circle the blazing hearts of galaxies. And galaxies themselves drift and rotate around each other in clusters so vast that light takes millions of years just to cross from one edge to the other. Everything caught in motion. Everything held in some invisible, ancient choreography. And the question that we are going to sit with tonight, slowly, gently, without any rush at all, is simply this. Why? What is this force, this pattern, this quiet law written into the fabric of the cosmos, that makes almost nothing in the universe sit perfectly still? Let your breathing slow now. There is no need to solve this tonight. There is only the need to wonder, to drift alongside the question the way a leaf drifts on a slow river, turning gently as it goes. Let us begin where all things seem to begin, in a cloud. Long before there was a sun, long before there was an earth for you to rest upon, there was only a vast, cold cloud of gas and dust, scattered thin across a stretch of space so enormous that our minds can barely hold its shape. This cloud was mostly hydrogen, the simplest and oldest element there is, mixed with faint traces of helium and grains of dust left behind by stars that had lived and died long before. And within this cloud, nothing much was happening. It simply existed, spread out, patient, quiet, cold. Some tiny irregularity, perhaps the shock wave from a distant exploding star, perhaps nothing more than the natural unevenness of matter itself, disturbed this stillness. And gravity, patient gravity, always pulling, always reaching, began to draw the cloud inward. Here is where the mystery begins to reveal itself. As that cloud collapsed, as its edges folded slowly toward its center, it did not fall straight in, like water down a drain with no motion of its own. It had, from the very start, the faintest whisper of rotation. A tiny drift, an imperceptible turning, so small it would have been impossible to measure. But as the cloud shrank, as its outer reaches pulled closer and closer to the center, that tiny whisper of a turn had nowhere to go. It could not simply vanish. And so, as the cloud tightened, that whisper became a murmur. The murmur became a hum. The hum became a spin. This is the shape of a law that governs the entire universe, a law we will come to know intimately as we drift deeper into tonight's journey, a law that explains why a figure skater pulls her arms inward to spin faster, why a spinning ball of pizza dough widens as it slows, why water may curl as it drains, and why, 4.5 billion years ago, a vast, sleepy cloud of gas began to turn faster and faster and faster as it collapsed inward upon itself, flattening, spreading, glowing faintly, with the first traces of heat. At the center of that swirl, something extraordinary and inevitable was being born. Somewhere in that flattening disk, in that widening ring of dust catching the earliest light of a not yet ignited star, tiny grains of matter were beginning to touch, to cling, to gather. And in the gentle darkness of that ancient turning cloud, in the same slow spinning motion that would one day become a day and a night, a spring and a winter, the seeds of every planet, every moon, and quite possibly every future. Dawn, drifting quietly there in the dark, waiting only for time to do what time does best. Let us stay here a while longer, in this ancient nursery of dust and gas, because there is no need to hurry toward the ending of this story. Picture it now, softly, the way you might picture a memory that isn't quite your own. A disk, vast beyond imagining, thin as a whisper compared to its width, spinning slowly around a center that glowed faintly, not yet a star, not yet anything with a name. Astronomers have a quiet term for this shape. They call it a protoplanetary disk. And though the word sounds clinical, almost cold, what it describes is something closer to a lullaby written in gravity and heat. A disk so wide it would have stretched many times past where your Earth would one day settle into its orbit, and within it, drifting in slow, patient spirals, were grains of matter no larger than specks of sand. For a very long time, nothing dramatic happened at all. This is important to sit with, because we often imagine the birth of worlds as violent, explosive, fast. But in truth, most of it was slow. Unbearably, beautifully slow. Grains of dust, carried along in that turning disk, would drift close to one another, touch, and sometimes, gently, cling together through the softest of static forces, the same kind of quiet attraction that makes a balloon stick to a wall or a sock cling to a sweater fresh from the dryer. Imagine that. The same small, humble force that tugs at your laundry was once, long ago, quietly building the first seeds of worlds. These tiny clumps grew slowly, grain by grain, pebble by pebble. And as they grew, so did their gravity, faint at first, then a little stronger, then stronger still, until these small wandering bodies, called planetesimals, began to pull in more material simply by existing, simply by being there in the path of the swirling disk. And here again, we return to that strange patient force we began with tonight. Spin. Because every planetesimal, every gathering clump of rock and ice, inherited the same rotation as the great disk that birthed it. Nothing in that disk was ever perfectly still, and so nothing born from it could be perfectly still either. Motion breeds motion. Turning breeds turning. It is passed down, quietly, like an inheritance no one asked for but everyone receives. Let your body settle a little deeper now into wherever you are resting. There is nothing you need to do but listen, and let this story drift over you the way starlight drifts over a sleeping field, felt more than seen. As millions of years folded slowly into one another, these planetesimals began to collide. Not violently, not always, though sometimes, yes, violently. But often it was a gentle merging, a soft accumulation, one small world folding into another, their combined gravity growing, their combined spin adjusting, blending, averaging into something new. Somewhere in this hush of slow cosmic time, one particular gathering of rock and metal, orbiting at just the right distance from the young, dim glow of the not yet fully formed sun, began to grow larger than its neighbors. It pulled in more dust. It pulled in more ice. It pulled in more of the debris that swirled endlessly around it. And with every collision, every merge, every small addition of mass, this growing world spun a little differently, a little faster in places, a little slower in others, until, at last, it settled into a rhythm all its own. This is the ancient, unwritten memory carried inside your Earth even now. Every rotation of this planet beneath you, every sunrise, every sunset, is an echo of collisions that happened billions of years before the first living cell ever stirred in a warm and shallow sea. Consider this softly, without any rush. The Earth beneath you, the ground holding you steady, the axis it quietly leans upon, all of it is the descendant of that same swirling disk, shaped by the same strange law of motion that we are only just beginning to uncover here tonight. Nothing about the spin of our world was decided in an instant. It was earned, slowly, through eons of gentle and sometimes violent gathering, until enough mass had come together, until enough momentum had been folded inward, that a new rhythm was born, one that has not stopped since, one that will not stop for a very long time to come. And yet, even now, even with the planet fully formed and spinning steadily in its place, we have still not answered the deeper question waiting quietly beneath all of this. We have seen that spin is inherited, passed down from cloud to disk to planet, but we have not yet asked what truly holds that spin in place once it begins. What is the deeper law, hidden in the mathematics of the universe, that makes a slow turn become an unstoppable one? To understand that, we must travel further inward, past the orbits of planets, past the swirling disk itself, down toward the very center of that ancient cloud, where something extraordinary was beginning to ignite in the dark, and where the true nature of this strange spinning force would finally reveal itself, waiting patiently in the crushing dark like a secret held since the beginning of time. Let yourself drift there now, gently, past the orbits of the young, half-formed worlds, past the drifting rubble of ice and rock, down through the thinning edges of that ancient disk, toward the center where all of this began. There, in that deep well of gravity, something remarkable had been happening all along, something so quiet and so slow that it would have been easy to miss if you were not looking closely, the way the most important things in life often are. At the heart of that swirling cloud, matter had been falling inward for a very long time. Hydrogen, mostly, the lightest and oldest element in the universe, drawn together grain by grain, wisp by wisp, compressing under its own gravity into a growing sphere. And as it fell inward, it carried with it the same whisper of rotation that had shaped everything else in that ancient disk. But here, at the center, something different was about to happen, something that would not simply spin, but would burn. This is a good place to pause and breathe. In, slowly, and out, even more slowly. There is no need to hold on to anything right now except the sound of this voice and the picture forming quietly in your mind. As more and more hydrogen gathered at the center of that collapsing cloud, the pressure at its core began to rise. Not gently, the way pressure rises in a room when a window is closed, but immensely, unimaginably, as trillions of tons of gas pressed inward from every direction at once. And with pressure came heat. Slowly, over what would have felt like an eternity to any observer, though there was no one there to observe it, the temperature at the center of this newborn ball of gas climbed higher and higher, past temperatures that exist nowhere on Earth, past anything we could recreate in our most powerful furnaces, until it reached a threshold long written into the laws of physics, a threshold near 10 million degrees, at which point something extraordinary occurred. Hydrogen atoms, pressed together with such unimaginable force, began to fuse. This is the moment a star is born. Not with a flash, not with a single dramatic instant, but with a slow, gathering ignition deep within a ball of gas that had been quietly falling inward for millions of years. Hydrogen fusing into helium, releasing light, releasing heat, releasing the very energy that would one day, billions of years later, warm a small blue planet and everything living upon it. And it is worth resting on this thought for a while. The warmth you may be feeling right now, wrapped in your blanket, settling into sleep, is a distant descendant of that first fire, carried across 93 million miles of empty space, born from a collapse that began in silence and finished in light. But here is where our strange force returns to the story, quietly, patiently, the way it always does. As that newborn star ignited at the center of the disk, it did not stop spinning. In fact, the very collapse that created it should have caused it to spin faster and faster, the same way a figure skater spins faster by pulling her arms inward. And yet, when scientists first studied our own sun, they found something puzzling. something that did not fit neatly into the story. The Sun, despite containing more than 99% of all the mass in our entire solar system, spins strangely slowly, taking about 27 days to complete a single rotation. If all that collapsing gas had simply spun faster and faster as it fell inward, the Sun should be spinning far more quickly than it does, so quickly, in fact, that it might have torn itself apart before it ever had the chance to ignite. So where did all that spin go? Let this question settle over you like a soft weight, pressing you gently deeper into rest. It troubled scientists for a long time, this quiet mismatch between what the mathematics predicted and what the universe actually showed them. Because angular momentum, that strange, invisible quantity tied to rotation, cannot simply vanish. It does not disappear. It does not evaporate into nothingness. If the Sun does not carry the spin that the collapsing cloud should have given it, then that spin must have gone somewhere else, transferred, redistributed, carried away and given to something else entirely. And this, quietly, gently, is where the story turns outward again, away from the star and back toward the swirling disk that surrounded it, toward the planets forming in the dark beyond, toward Jupiter, vast and slow, toward the outer world still gathering themselves from ice and dust, because it is there, in the almost unnoticed transfer of motion from the newborn Sun into the disk around it, that the true nature of this force begins to reveal something far stranger than anyone expected. Something that reaches beyond fusion, beyond gravity, into the deeper architecture of the universe itself, the part written not in fire, but in motion. Let yourself sink a little further now, past the surface of the Sun, past its slow and steady glow, out into the quiet space that surrounded it in those early days, the space still thick with leftover gas, still swirling with the faint magnetic breath of a newborn star. Because this is where the missing spin was hiding all along, not lost, never lost, only carried away, gently, invisibly, along threads of magnetism reaching out into the dark like long, unseen fingers. A young star is not a quiet thing, even in its slowest moments. As it forms, it generates a magnetic field, vast and unseen, looping out from its surface and into the disk of gas still spinning around it. And where that magnetic field met the charged particles drifting through that disk, something remarkable happened. The field lines acted almost like invisible threads, tethering the star to the slower-moving material further out. And just as a rope pulls taut between two objects moving at different speeds, these magnetic threads pulled at the star's rotation, slowing it down, while gently nudging the outer disk to spin a little faster, carrying that borrowed momentum outward, away from the center, into the cold, wide reaches where the planets were still being born. This is called magnetic braking, and it is one of the quiet, hidden reasons our Sun spins as slowly as it does today. Rest with that for a moment. The very thing keeping our star calm, steady, and long-lived, rather than spinning itself into a violent, short-lived frenzy, was this invisible exchange of motion, passed from star to disk, through threads of magnetism too faint for any eye to ever see. And it is worth remembering, as you drift here in this thought, that none of this motion was created from nothing. That is a rule that reaches through the entire universe, one of the oldest and most unshakable laws in all of physics. Motion is never made from emptiness, and it is never erased into emptiness either. It only moves. It only transforms. It only shifts from one place to another, from one body to another, the same way warmth moves from a flame to the air around it, without ever truly vanishing. This is the deeper secret behind our strange spinning force tonight, a secret we are only just beginning to touch. Picture now, if you will, the outer edges of that ancient disk, far beyond where the Sun's light had grown thin and pale, where the cold was deep enough for ice itself to form solid grains rather than vapor. It was here, in this dim and distant region, that the giant planets began to take shape, Jupiter first among them, gathering gas and ice into a body so massive that it would one day account for more mass than all the other planets in our solar system combined. And Jupiter, born from that same turning disk, born from the same silent inheritance of spin passed down since the beginning, would become one of the fastest rotating planets we know, completing a full turn in less than 10 hours despite being more than 11 times wider than Earth. Let that settle over you slowly. A world so vast that 1,000 Earths could fit inside it, spinning so quickly that its own clouds are stretched into long, streaking bands of amber and cream, chasing each other endlessly around its enormous girth. This is not chaos. This is not randomness. This is the same law, the same quiet inheritance, simply expressed on a scale so much larger than our own that it becomes almost impossible to hold in the mind without a little bit of wonder pressing gently against the edges of sleep. And it is here, in the space between our slow, steady sun and its wild, spinning giant of a planet, that we begin to see the outline of something even larger than our solar system, something that stretches far beyond the reach of any single star or any single family of worlds. Because if spin is inherited, if it is passed down, transferred, and reshaped, but never created and never destroyed, then somewhere, long before our sun ever began to collapse from its quiet cloud of gas, something else must have been spinning too. Something vast enough, old enough, and patient enough to have given that first whisper of rotation to the cloud itself. And to find the origin of that whisper, we must travel far beyond the edges of our solar system altogether, out into the star-filled dark, into the slow, turning arms of the galaxy that has cradled our sun for the entirety of its long and quiet life, a galaxy that carries within it a mystery even deeper than the one we have been circling ever since we began. So let us drift there now, slowly, the way starlight drifts across the space between things, unhurried, patient, taking its own sweet time to arrive. Picture the galaxy from above. Though no one has ever truly seen it this way, no eye, no lens, no wandering spacecraft has risen high enough above the galactic disk to look down and see the whole shape of home. And yet we know its form, pieced together from radio waves and starlight, from the patient decades of astronomers tracing the positions of stars the way a person might trace the shape of a room in the dark, one careful hand against the wall at a time. And what emerges from all that careful tracing is a shape both familiar and strange. A vast pinwheel of light, 100,000 light years from one edge to the other, its arms curling outward in long luminous spirals, each one a river of stars, gas, and dust, all of it turning, slowly, ponderously, around a center so dense and so dark that light itself struggles to escape its grip. And there, at the heart of that turning galaxy, lies a truth almost too strange to hold on to for very long. Because the very center of the Milky Way, the pivot point around which every star, every planet, every wisp of interstellar cloud slowly revolves, is not a place of light at all. It is a black hole. Sagittarius A star, they call it, a name too clinical for something so enormous, so quietly terrifying in its patience. A black hole with a mass some 4 million times that of our Sun, folded down into a space smaller than the orbit of Mercury, an object so dense that space and time themselves seem to lose their footing near its edge. And it is around this dark, silent center that our entire galaxy turns. Every star we can see in the night sky, every constellation that has guided sailors and poets and lovers for as long as there have been eyes to look up, all of it is caught in a slow, inexorable orbit around a point of absolute darkness. Our own sun, along with its small, spinning family of planets, takes roughly 230 million years to complete a single circuit around the galactic center. 230 million years, a span of time so vast that the last time our solar system was in its current position, in this exact place in its long galactic orbit, dinosaurs had not yet appeared on Earth. Continents were arranged in configurations we would not recognize. The very shape of the world was different, and yet the sun kept moving, kept turning, kept tracing its slow ellipse around a black hole it will never see, will never touch, and yet obeys with perfect, silent fidelity. And here, in this picture, the mystery of spin grows even stranger, because a black hole, in all its darkness, all its crushing gravity, cannot itself explain why the galaxy turns the way that it does. Gravity alone, if it were the only force at work, would allow stars near the center to sweep around quickly, and stars at the edges to lag far behind, the way planets in our own solar system slow their pace the farther they drift from the sun. And yet, when astronomers measured the speeds of stars at the outer edges of the Milky Way, in the thin, faint reaches of the galactic disk, they found something that should not have been possible. Those outer stars were moving far too fast. Fast enough that by every law of gravity as we understood it, they should have been flung outward into the void, scattered like sparks from a spinning wheel, the galaxy itself unable to hold together. But it does hold together. It has held together for over 10 billion years, spinning steadily, gracefully, as though some unseen hand were cupped around its edges, some invisible scaffold keeping every star bound to its slow and stately orbit. And so scientists came to a conclusion that still, to this day, unsettles even those who have spent entire careers studying it. That the galaxy is not made of what we can see. That the stars, the gas, the dust, the black hole at its center, all of it together accounts for only a small fraction of the mass required to explain the motion we observe. The rest, the vast, overwhelming majority of what holds the Milky Way together, is something we cannot see at all. Something that does not shine, does not reflect, does not interact with light in any way we have yet discovered. They named it, with a kind of quiet honesty, dark matter, an admission that we know it is there by its gravity alone, by the way it shapes the turning of galaxies, by the way it whispers to starlight and bends it around massive clusters, and yet we cannot say, even now, what it actually is. And so the galaxy turns, cradled not by what glows, but by a vast, invisible architecture of something else entirely, something that outweighs every star combined, something that surrounds the Milky Way in an unseen halo stretching far beyond even the outermost reaches of its spiral arms, something that may in fact be the very thing that first gathered the primordial gas of the universe into the great turning disk we now call home, long before the first star ever ignited, before the first cloud of hydrogen ever began its long, slow collapse into light. Because if we follow the story back far enough, past the black hole, past the spiral arms, past even the first stars that ever burned in the darkness, we arrive at a time before galaxies existed at all. A time when the universe was young, still smoothing itself out from the impossible heat of its own birth, a thin, nearly uniform mist of hydrogen and helium drifting through an expanding dark. Nearly uniform, but not quite. And it is in that tiny imperfection, that whisper of unevenness, that the entire story of spin, of galaxies, of stars, of us, finds its true beginning. Because a perfectly smooth universe, one where every particle of gas was spread with flawless mathematical evenness, would have stayed that way forever. Gravity would have had nothing to pull toward, no denser pocket to gather itself around, no seed from which to grow a single star. But the universe was not perfectly smooth. From the very first fractions of a second after its birth, tiny quantum fluctuations, ripples so small they defy easy comprehension, were stretched and magnified by the rapid expansion of space itself, leaving behind faint variations in density, some regions only a little thicker with matter than others, differences so slight that if you could have stood within that early universe and looked out at the gas around you, you would have seen nothing but uniform darkness in every direction. And yet those tiny differences were enough. Enough for gravity to begin its slow, patient work, pulling the slightly denser regions inward, drawing matter toward those faint gravitational wells the way water gathers first in the shallowest parts of a landscape before it finds its way into rivers. And it was dark matter, that same invisible substance now cradling the spinning arms of our galaxy, that led this process from the very beginning. Because ordinary matter, the hydrogen and helium that would one day become stars and planets and living things, was still hot, still energetic, still bound up in a searing plasma that resisted collapse. But dark matter felt none of that heat, answered to no force but gravity itself, and so it began to gather first, forming vast, invisible scaffolds throughout the early universe, great tangled webs of gravitational wells stretching across unimaginable distances, a hidden architecture drawn entirely in the language of mass and attraction, long before there was any light to reveal its shape. And ordinary matter followed. Slowly, over hundreds of millions of years, the hot gas of the early universe cooled enough to fall into those waiting gravitational wells, pooling within the dark scaffolding the way mist settles into the low places of a valley at dusk. And it is here, in these vast pools of gathering gas, that the story of spin truly begins. Because as gas fell inward from every direction, from all the surrounding reaches of space, it did not fall in perfectly straight lines toward a single center. Some of it arrived from slightly this direction, some from slightly that one, each stream carrying with it a small, almost imperceptible sideways motion, a residue of the uneven, turbulent conditions of the early universe. And when countless streams like this converge upon a single gathering cloud, their combined sideways motions do not simply cancel out into stillness. They average into a net rotation, a slow, collective turning, born not of any single push or pull, but of the accumulated asymmetries of everything that fell inward together. This is, astronomers believe, the true origin of galactic spin, a concept they call tidal torque, the idea that neighboring clumps of matter in the early universe, still connected to one another by faint gravitational threads, exerted small twisting forces on each other as they grew, nudging the collapsing gas into a slow rotation before it had ever formed a single star. It is a strange thing to consider that the spin of an entire galaxy, the very same spin that will one day cradle a sun, and that sun a planet, and that planet a spinning blue world where someone lies in the dark listening to a story about spinning, was set in motion not by any single event, not by any dramatic collision or explosion, but by the quiet, cumulative influence of a universe still learning how to be uneven with itself. And so the gas continued to gather, continued to slowly turn, drawing inward under the patient hand of gravity, spinning faster and faster the way a skater draws their arms in close, faster now, tighter now, until at last, deep within the swirling heart of that primordial cloud, the pressure and heat became too great for the gas to bear any longer. And in that moment, in some ancient, forgotten pocket of the early universe, the first light the cosmos had ever known outside of its own explosive birth began to kindle. The very first stars. Born already spinning, already inheriting a motion passed down from the turbulence of creation itself, and it is to those first stars, and the strange luminous families they gathered around themselves, that we must now turn our attention, because their story is, in many ways, the story of everything that came after, including the quiet, spinning world beneath you now, the one holding you gently as you listen. Picture that first generation of stars, born from clouds of nearly pure hydrogen and helium, untouched by the heavier elements that would later come to fill the universe, elements that had not yet been made, because nothing had yet lived long enough, or died violently enough, to forge them. These first stars, astronomers call them Population 3, though no one has ever seen one directly, their existence known only through careful inference, through models and calculations and the faint, indirect echoes they may have left behind in the light of the universe's earliest years. They would have been unlike any star that exists today, some of them perhaps hundreds of times the mass of our sun, burning with a ferocity almost impossible to comprehend, blue-white and blinding, living fast and dying faster, their lives measured not in the billions of years that a star like our sun enjoys, but in mere millions, sometimes less. And when they died in the most consequential way a star can die. Because massive stars do not simply fade. They collapse, suddenly and catastrophically, their cores crushing inward under their own weight until the outer layers rebound in a violence so complete it briefly outshines entire galaxies. Supernovae, we call them now, though the word feels too small for what actually happens, a single point of light in the sky where, for a few weeks, the energy released could rival the combined light of billions of ordinary stars. And it is in the heart of that violence, in the crushing pressures and searing temperatures of a dying star's final moments, that the heavier elements of the universe are forged. Carbon, oxygen, iron, silicon. all of it born in the death throes of stars that lived and burned long before our sun was ever a whisper of gas drifting through the dark. And when those first stars died, they scattered these newly forged elements outward into space, seeding the surrounding clouds of hydrogen and helium with something they had never possessed before, the raw material for rocky worlds, for oceans, for the slow chemistry that would one day, unimaginably far in the future, become life itself. And as this enriched gas drifted outward from the wreckage of those first dying stars, it did not simply scatter into random disorder. It carried with it, still, the same inherited spin that had shaped the clouds from which those very first stars had formed, the same slow rotation set in motion by tidal torques in the early universe, passed down now, like a family heirloom, into the next generation of star-forming clouds. And so began a long, patient cycle that would repeat itself again and again across billions of years, a rhythm as old as the galaxy itself. Clouds of gas collapsing under gravity, spinning faster as they contracted, giving birth to stars, some of those stars living briefly and violently before scattering their newly forged elements back into the surrounding dark, enriching the next generation of clouds, which would themselves collapse and spin and ignite, each cycle adding a little more heavy material to the mix, each generation of stars carrying forward a little more of the chemistry needed for planets, for rock, for water, for the delicate architecture of living things. By the time our own sun began to form, some 9 billion years after the universe itself was born, this cycle had already repeated itself countless times throughout the galaxy. The cloud of gas from which our sun eventually collapsed was not the pure, simple hydrogen of the earliest universe, but something far richer, seeded by the deaths of generations of stars long extinguished, carrying within it not just hydrogen and helium, but carbon and oxygen and iron and silicon and every other element needed to build not only a star, but the rocky planets that would come to orbit it. And it carried, too, that same inherited spin, that same slow rotation passed down from cloud to star to supernova to cloud again, an unbroken thread of motion stretching back through billions of years, back through countless dying and reborn stars, back through the first pinwheel structure of the galaxy itself, back to those tiny quantum fluctuations in the first fractions of a second after the universe began. It is a strange kind of inheritance to consider, lying here in the dark, feeling still and motionless as you rest. Because the very atoms that make up your body, the carbon in your blood, the calcium in your bones, the iron carried in every red cell that moves quietly through you even now, all of it was forged inside the heart of some ancient, long-dead star, flung outward in a final act of violence, gathered again into a cloud that carried, still, the whisper of a rotation set in motion at the very beginning of time, a rotation that shaped a galaxy, and a solar system, and a sun, and a spinning blue world, and now shapes the slow, steady rhythm of your own breathing as you drift, unaware, toward the deep and patient sleep that waits for you at the end of all this listening. Let us return, now, to that particular cloud, the one that would one day become our sun, our earth, and everything that has ever lived upon it. Picture it drifting through the galaxy some 4.5 billion years ago, a vast, cold expanse of gas and dust many light years across, so thin in most places that it would have registered as a near vacuum, and yet massive enough, when taken as a whole, to one day give birth to an entire star system. It drifted quietly, slowly, carrying within it that same faint rotation inherited from the larger turning of the galaxy, a rotation so gentle, so subtle, that nothing within the cloud itself could have felt it, the way you cannot feel the Earth turning beneath you even now, though it carries you around its axis at nearly 1,000 miles an hour. And then, something disturbed it. Astronomers still debate exactly what that disturbance might have been. Perhaps the shock wave from a nearby supernova, the death cry of another massive star sending a wave of compressed gas rippling outward through the galaxy, striking our quiet cloud and pressing it inward. Perhaps the slow gravitational pressure of the cloud passing through one of the galaxy's spiral arms, those great luminous rivers of stars and gas that circle the galactic center, regions of higher density where clouds are gently squeezed simply by drifting through them, the way a slow-moving fog might thicken as it passes through a narrow valley. Whatever the cause, something pushed against that ancient cloud, and gravity, ever patient, ever waiting for the smallest opportunity, took hold. And so, slowly, almost imperceptibly at first, the cloud began to collapse. Not evenly, not all at once, but unevenly, the way water gathers first into small pools before finding its way into a single stream. Denser pockets within the cloud began to draw in the gas and dust around them, growing heavier, growing stronger in their gravitational pull, drawing in more material still. And as this collapse continued, that faint, inherited rotation, the same rotation passed down from tidal torques in the early universe, from the slow turning of the galaxy itself, began to matter in a way it never had before. Because a cloud that is collapsing while also rotating cannot collapse evenly in every direction. Gravity pulls inward from all sides equally, but rotation resists that inward pull most strongly along the plane of its spin, the same way a spinning bucket of water resists being poured out sideways, its contents pressed outward toward the rim by the sheer momentum of the spin. And so, as our cloud collapsed inward along its rotational axis, drawing closer and closer together above and below, it could not collapse nearly so easily around its equator, where the outward momentum of that same slow rotation pushed back against the crushing weight of gravity. And so the cloud began to flatten, transforming slowly from a vast, roughly spherical mass of gas into something closer to a disk, a great swirling pancake of material with a dense, glowing knot of gas and dust gathering at its very center, the seed of what would become our sun. This is the same conservation of momentum we spoke of earlier, the same principle that spins a figure skater faster as she draws her arms inward, now playing itself out on a scale almost too vast to comprehend, a cloud many trillions of miles across collapsing down into a system that would one day fit comfortably within the orbit of a single dwarf planet. As the cloud contracted, its rotation had nowhere to go, no way to simply vanish, and so it had to speed up, the same fixed quantity of spin now confined to an ever-shrinking space, until that early, gentle rotation of the interstellar cloud transformed into something far more dramatic, a swirling, spinning disk of gas and dust turning at tremendous speed around the newly forming sun at its heart. And it is within this spinning disk, this protoplanetary disk as astronomers call it, that our entire solar system would eventually take shape. Not created separately, not formed by some other process entirely distinct from the birth of the sun itself, but grown directly out of the same swirling material, the same inherited rotation, the leftover gas and dust that did not fall into the sun's core but remained suspended in that great turning disk, slowly clumping together, colliding, merging, growing from grains of dust into pebbles, from pebbles into boulders, from boulders into the first small worlds that would one day become planets. Every single planet in our solar system, every moon, every asteroid, every comet drifting through the dark reaches beyond Neptune, all of it formed from this one spinning disk, and all of it, as a direct consequence, inherited the same fundamental direction of rotation, the same tilt, the same underlying order that had been set in motion by a cloud collapsing under gravity's patient hand some 4.5 billion years ago. And so when you look up, even now, even tonight, and you see the moon rise in a certain direction, and you see it trace a certain path across the sky, you are not looking at randomness. You are looking at memory. You are looking at the fossil record of a collapse that happened before there was an earth to stand on, before there was a sky to look up into at all. Consider, for a moment, what this means for the moon itself. The moon does not simply drift through space beside us, a passive companion caught in Earth's gravity. The moon orbits in nearly the same plane as the planets circle the sun, tilted only slightly, a small deviation from the disk's average, the kind of gentle imperfection you would expect from a system built not by design but by countless collisions, each one nudging the average this way or that, none of them powerful enough to erase the underlying pattern entirely. And this is true again and again as you move outward through the solar system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, each one circling the sun in the same direction, each one occupying roughly the same flattened plane, like marbles pressed into the surface of a spinning record, all of them turning together, all of them keeping time to a rhythm none of them chose, a rhythm inherited from the disk they were born inside of. Even the asteroids follow this same quiet law. The asteroid belt, that scattered ring of rubble between Mars and Jupiter, is not the wreckage of a destroyed planet, as old stories once imagined, but rather the leftover material that never managed to gather itself into a single world, kept apart, astronomers believe, by the immense gravitational influence of Jupiter nearby, stirring the orbits of anything that tried to grow too large, too fast. And yet, even in this scattered debris, this cosmic rubble field, the same rotational memory persists. The asteroids orbit the Sun in the same direction as the planets. They occupy, for the most part, that same flattened disk. They are, in a very real sense, siblings to the planets, unfinished siblings, worlds that began the long process of becoming but were interrupted before they could complete it. And then there are the comets, drifting in from the outer dark, from the Kuiper belt just beyond Neptune, and from the even more distant, more mysterious Oort cloud, a vast spherical shell of icy bodies thought to surround the entire solar system at almost unimaginable distance, so far out that some comets take millions of years to complete a single orbit around the Sun. These distant wanderers behave differently. Their orbits are often tilted at extreme angles, sometimes nearly perpendicular to the plane where the planets travel, sometimes even moving in the opposite direction entirely. And this difference itself is a kind of evidence, a clue in the ongoing scientific story of how our solar system came to be shaped the way it is. Because the comets of the Oort cloud are thought to have been flung outward long ago, scattered by gravitational encounters with the young giant planets, thrown clear of the orderly disk and into looser, wilder, more chaotic paths, carrying with them a memory not of gentle inheritance but of violent departure, of a solar system still settling into itself, still finding its long-term balance in those early turbulent centuries. So even the exceptions tell the same underlying story. Order first, chaos second, inheritance interrupted by encounter. This is the pattern that seems to repeat throughout the universe wherever gravity is given time and material enough to work with. Rotation is not imposed from without. It emerges from within, a natural consequence of collapse, of conservation, of the same physical law that spins a figure skater faster as her arms draw inward toward her chest. Nothing about this required a designer. Nothing about this required an intention. The angular momentum was already present in the diffuse, slowly turning cloud long before it ever began to collapse, and everything that followed, the flattening, the disk, the planets, the moons, the asteroids, the comets, was simply that dot momentum finding its shape, finding its geometry, finding a way to express itself given the raw materials available. And you, reading or listening to these words now, are a physical descendant of that process. Every atom in your body was forged in some ancient star, scattered across the galaxy in that star's eventual death, gathered up again in the slow turning of this solar nebula, incorporated into the growing Earth, and eventually, through the impossibly long and patient work of biological evolution, arranged into the particular structure that allows you to be conscious, to wonder, to ask questions about the very forces that made your own existence possible in the first place. You are not separate from this story. You are the universe's way of turning slowly enough and long enough to eventually ask why it spins at. And that question, simple as it sounds, carries within it an entire hidden universe of physics, one that stretches far beyond our own solar system, far beyond the quiet corner of the galaxy where our sun happens to burn. Because the same forces that shape the disk around our infant star are, at this very moment, shaping countless other disks around countless other stars, scattered across the Milky Way, scattered across galaxies so distant that their light left home before the Earth itself had even finished cooling. Rotation, it seems, is not a peculiarity of our own small corner of existence. It is a signature written into the very architecture of matter, repeating itself wherever gravity finds gas, wherever gas finds time, wherever time is allowed to stretch long enough for collapse to do its slow and patient work. Astronomers have, in recent decades, actually observed these other disks directly, capturing images of young stars still wrapped in their swirling nurseries of gas and dust, disks glowing faintly in infrared light, spinning in exactly the pattern our own solar nebula must have spun some 4.5 billion years ago. One of the most striking examples come from a young star system named HL Tauri, observed by the Atacama Large Millimeter Array High in the Chilean desert, where astronomers detected not a smooth, undifferentiated disk, but one carved into distinct concentric rings, dark gaps separating them, gaps thought to mark the locations where planets are actively forming, sweeping up material along their orbits the way a snowplow clears a path down a street. To look at that image is to look, quite literally, into the past, into a mirror of what our own solar system must have resembled in its own extreme youth, when the Earth itself was nothing more than a gap in a ring, a whisper of gravity gathering dust unto itself in the dark. And this returns us to that deeper, quieter question, the one lying beneath all of this observation and calculation. Why does the universe favor rotation at all? Why not simple, formless collapse, gas falling straight inward toward a single point, compressing into a sphere and nothing more, no disk, no spin, no planets? The answer, as with so much in physics, traces back to a law so fundamental that it governs everything from the spiral of a hurricane to the spin of a subatomic particle, from the twirl of a ballerina to the majestic slow wheel of an entire galaxy turning in the dark. This law is called the conservation of angular momentum, and it states, with a simplicity that almost feels too elegant to be true, that in the absence of outside forces, the total angular momentum of a system remains unchanged. It does not disappear. It does not fade. It merely transforms, redistributes, concentrates, or spreads, but the total quantity abides, indifferent, unbreakable, silently obeyed by every particle in creation whether it knows the law exists or not. To understand what this truly means, imagine again that figure skater, arms extended, spinning slowly across the ice. As she pulls her arms inward toward her body, something remarkable happens. She spins faster. Not because she has exerted some new force to accelerate her rotation, not because she has added energy to the system, but because she has changed her shape, and in changing her shape, she has forced the same fixed quantity of angular momentum to express itself differently. Angular momentum depends not only on how fast something spins, but on how that mass is distributed around the center of rotation. Spread the mass wide, and the same angular momentum expresses itself as a slow, graceful spin. Pull that mass close, concentrate it, gather it near the axis, and that same fixed quantity is forced to intensify. The rotation must accelerate to conserve the whole. This is not a metaphor. This is not artistic license borrowed from physics and softened for poetry. This is the literal, quantifiable law by which our entire solar system, and countless others besides, came into being. The molecular cloud that would one day become our sun and its planets was, in its earliest form, almost too vast to imagine, a scattered breath of gas and dust spanning many light years across, rotating so slowly, so imperceptibly, that if you had stood within it, you would have felt nothing, seen nothing, sensed no motion at all. And yet that cloud was rotating. Every cloud in the galaxy inherits some trace of rotation, some faint imprint of the greater galactic wheel it orbits within, the same way a small eddy in a river carries within it some memory of the river's larger current. This rotation was almost immeasurably small, a whisper of angular momentum distributed across trillions upon trillions of miles of nearly empty space. But it was there. It was real. It was waiting. And then, gravity began its slow work. Grain by grain, particle by particle, the cloud began to draw inward upon itself, collapsing under its own weight, shrinking from something the size of many solar systems into something far smaller, far denser, far more concentrated. And as it collapsed, that ancient law asserted itself with quiet, mathematical certainty. The angular momentum could not vanish. It could only concentrate, the way the skater's arms draw inward, the way a slow drifting whisper becomes, through sheer compression, an unmistakable, undeniable spin. What had once been a rotation so faint it could not have been measured by any instrument became, through collapse alone, a turning so pronounced that it would eventually flatten an entire cloud into a disk, would eventually cast off planets like sparks from a grinding wheel, would eventually give rise to days and nights, to seasons, to the turning of a single blue world around a single yellow star. This is the strange alchemy at the heart of it all. Nothing was added. No outside hand reached in and set anything spinning. The rotation was always present, dormant, latent, waiting patiently across unimaginable stretches of time for gravity to draw it out, to concentrate it, to reveal what had been hidden in plain sight since the cloud itself first drifted into being. And here it is worth pausing, worth letting the mind rest a while on the sheer strangeness of this idea, because there is something almost dreamlike in the notion that spin can be conjured from stillness simply by the act of shrinking. We do not feel this in our daily lives, not in any obvious way, because the objects we interact with are too small, too light, too loosely bound to gravity's demands for the effect to become visible. But scale the process up to the size of a solar nebula, give it billions of years and the patient, relentless pull of gravity, and the invisible becomes undeniable. The imperceptible becomes architecture. The whisper becomes a wheel. This is why astronomers, when they search the galaxy for stars still being born, expect to find disks. Not because disks are aesthetically pleasing, not because nature enjoys symmetry for its own sake, but because the mathematics leaves no other reasonable outcome. Any cloud with even the faintest trace of rotation, when compressed by gravity, must flatten. It cannot collapse into a perfect, motionless sphere any more than a marble balanced perfectly on a needlepoint could remain there forever, undisturbed by the smallest imaginable breath of air. Physicists sometimes describe this using the image of a spinning pizza dough, tossed and stretched by a skilled hand until it thins into a wide, flat disk of dough hanging in the air. The motion of the toss encourages the dough to spread outward and flatten, centrifugal tendencies fighting against the dough's own cohesion, finding a compromise in that recognizable circular shape. Something remarkably similar occurs on a cosmic scale, though shaped by gravity rather than human hands, though spanning millions of miles rather than a few feet of kitchen air. Material closer to the central axis of rotation moves faster, is flung outward more forcefully, while material along the poles of the collapsing cloud, above and below the plane of rotation, does not benefit from this outward centrifugal support. The result is a slow but inevitable flattening, matter draining down out of the upper and lower regions, spiraling inward and outward simultaneously, until only the wide equatorial disk remains, spinning steadily like some enormous cosmic pinwheel of gas, dust, and slowly gathering destiny. It is worth remembering, too, that this is not merely a story told about the past. It is a story still unfolding, still observable, still happening at this very moment across the galaxy. Somewhere out there, in some quiet, unremarkable pocket of interstellar space, a cloud not so different from the one that birthed our own sun is, right now, in the earliest stages of the same collapse. Somewhere a faint, imperceptible rotation is beginning its slow transformation into something larger, something more defined, something that will one day cast off gas giants and rocky worlds of its own, will spin a debris field into planets, will perhaps, in some far distant and unknowable future, give rise to conditions capable of sustaining something we might recognize, however distantly, as life. And whether or not anything in that distant system ever becomes conscious enough to look outward and wonder about its own origins, the physics will not care, will not wait, will not pause for meaning. It will simply proceed, indifferent and exact, the same immutable law of conservation quietly dictating the outcome regardless of whether anyone is present to observe it, to name it, to marvel at it. This is one of the strange and humbling truths embedded within the study of angular momentum, one that becomes clearer and more profound the longer you sit with it in the quiet stillness of night. The universe does not require witnesses. It does not perform its rotations, its collapses, its formations for an audience. It simply follows the rules that were set, in some sense, from the very beginning, rules baked into the fundamental relationship between mass, motion, and distance from a center, playing out with total indifference across scales ranging from the subatomic to the intergalactic. Electrons carry angular momentum in their strange quantum spin, a property so alien to ordinary intuition that physicists still debate how best to visualize it. Planets carry angular momentum in their orbits and their daily rotations. Galaxies carry angular momentum in their majestic slow wheel through the dark, spiral arms tracing the same fundamental principle across hundreds of thousands of light years. And somewhere in between all of these vast and impossibly small extremes sits our own quiet blue world, spinning once every 24 hours, carrying its own small portion of angular momentum inherited from a cloud that began collapsing long before there were eyes to see it, long before there was a mind capable of asking what any of it meant. Consider, for a moment, the earth beneath your feet, or beneath wherever you happen to be resting now, in this quiet hour of listening. It does not feel as though it is moving. It does not feel as though you are, at this very moment, being carried around the planet's axis at a speed of roughly 1,000 miles per hour. If you happen to be somewhere near the equator, slower as you move toward the poles, but still turning, still spinning, still obedient to the same law that shaped the solar nebula billions of years ago. This is one of the quiet miracles of inertia, another close companion of angular momentum, the reason you do not feel the Earth's rotation the way you might feel the sudden lurch of a car turning a sharp corner. You are moving with the Earth, matched perfectly to its rotation, carried along smoothly, evenly, without friction, the way a passenger in a smoothly gliding train does not feel the individual turning of the wheels beneath them. And yet the rotation is there, real, measurable, responsible for the alternating rhythm of day and night that has shaped the evolution of nearly every living creature on this planet, shaped the rise and fall of temperature, shaped the internal clocks ticking quietly within every cell of your body, synchronized, however imperfectly, to a spin that began long before life itself ever emerged from the primordial seas. This rotation, too, is not eternal, not fixed, not immune to the same slow processes of change that govern everything else in this unfolding cosmic story. The Earth's spin is gradually slowing, almost imperceptibly, stretched thin across timescales so vast that a single human lifetime could never hope to notice the difference. The culprit, in this case, is not some external force acting from outside the Earth-Moon system, but rather an internal transfer, a slow and patient exchange of angular momentum between the Earth and its companion the Moon, mediated by the gentle but relentless pull of tidal forces. The Moon's gravity does not simply pull on the Earth as a whole. It pulls more strongly on the side of the Earth nearest to it, and more weakly on the side farthest away, creating a subtle stretching, a tidal bulge in the oceans that rises and falls with the Moon's position overhead. Because the Earth rotates faster than the Moon orbits, this tidal bulge is dragged slightly ahead of the Moon's position, a small misalignment that creates a gentle gravitational tug backward on the Earth's rotation, slowing it by the barest fraction of a second every century, so gradual a change that it takes careful measurement of ancient eclipses, recorded by astronomers thousands of years ago, to even detect the shift at all. But angular momentum, as we have already learned, cannot simply vanish. It can only transform, redistribute, move from one part of a system to another. And so as the Earth's rotation slows, ever so slightly, that lost angular momentum does not disappear into nothingness. It is transferred, instead, to the Moon, and the Moon, receiving this quiet gift of momentum, responds in the only way physics allows. It moves slowly outward, spiraling away from the Earth at a rate of roughly 1.5 inches per year, an almost absurdly small distance, and yet one that adds up, over the vast stretches of geological time, to something significant. Billions of years ago, in the early history of the Earth-Moon system, the Moon orbited far closer than it does today, close enough that tidal forces would have created oceanic tides of staggering height, closer than we can easily imagine standing on a beach and looking up into a night sky. And billions of years from now, the Moon will continue its slow retreat, drifting ever further from the Earth, the days growing ever so slightly longer as this ancient exchange continues its patient, silent work. There is something profoundly beautiful in this, something that rewards quiet contemplation rather than urgent analysis. The Earth and the Moon are locked, even now, in a slow gravitational dance that has been unfolding for over 4 billion years, a conversation conducted not in words but in the subtle language of tidal forces and angular momentum, each partner shaping the other, each partner responding to the other's presence, neither one able to act entirely independently of the other's gravitational influence. And this dance, too, traces its origins back to that same ancient collapse, that same initial disk of gas and dust that gave rise to the Earth in the first place, for the leading scientific explanation for the Moon's very existence suggests that it did not form separately from the Earth at all, but was born out of a cataclysmic collision, sometime in the earliest, most violent chapter of our planet's history, when a body the size of Mars, a wanderer that scientists have come to call Theia, moved through the crowded and chaotic architecture of the young solar system and found itself, whether by inevitability or by chance, on a collision course with the newly forming Earth. Picture it, if you can, though picturing it will only carry you so far, because the scale of that event resists the imagination the way the scale of the universe resists it, the same fundamental humility that has followed us through every part of this story. Picture a world, still glowing, still remembering its own formation, still settling into the shape gravity had chosen for it, and picture another world approaching not with malice, for there is no malice in physics, only momentum, only mass, only the blind unfolding of trajectories set in motion long before either body existed as anything more than scattered material in a swirling disk. And then, picture the moment of contact, though contact is too gentle a word for what happened, too small a word for an event that would reshape not one but two worlds in a single cataclysmic instant. The collision, when it came, would have been unimaginable in its violence, a release of energy so vast that it defies ordinary comparison, vaporizing rock, melting stone, hurling molten debris outward into space in a great glowing arc, a wound in the fabric of the newly formed Earth that would take shape, over time, into something entirely unexpected. Theia itself, in most versions of this story, did not survive as a separate body. It was consumed, absorbed, its material merging with the material of the young Earth in a violent marriage of iron and rock and silicate, a merging so thorough that even now, billions of years later, scientists searching for the chemical signatures of that ancient impactor find them woven so deeply into the Earth's own composition that separating one from the other becomes almost impossible. In some sense, then, we are already partly Theia. The iron in the planet's core, the rock beneath our feet, may carry within it the ghost of a world that no longer exists as itself, a world that gave up its separate identity so that something new could be born from wreckage. And out of that wreckage, out of that ring of debris flung into orbit around the wounded, reforming Earth, the Moon began to take shape. Not slowly, not over the vast stretches of time we associate with most cosmic processes, but with a strange and startling speed, the debris coalescing, gravity once again performing its quiet work of gathering scattered material into a single coherent form, until what had been a chaotic ring of molten fragments became a sphere, glowing, close, achingly close to the Earth in those earliest days, orbiting at a distance perhaps only a tenth of what separates the two worlds now. Try, for a moment, to imagine that sky. Not the sky we know, not the pale, familiar disk that rises each night with its comforting and unchanging face, but a moon so near that it would have dominated the heavens, filling a vast portion of the horizon, its gravitational grip on the young Earth so powerful that the tides it raised would have been almost violent in their intensity, the oceans, still forming, still finding their shape, rising and falling with a ferocity that no shoreline has known since. The days themselves were shorter then, the Earth spinning more quickly on its axis, unburdened by the slow gravitational braking that the Moon's presence would impose across the coming eons, and it is in this braking, this steady transfer of energy between two bound and dancing worlds, that we find our way back to the deeper subject of this meditation, back to that invisible force we have been circling from the very beginning, back to spin itself, and to the ways in which even the moon, born from catastrophe, exists today as a living record of angular momentum's quiet, ceaseless conservation. For the moon does not simply orbit the Earth in some fixed and static arrangement. It is drifting, slowly, imperceptibly, but undeniably, moving outward from the Earth at a rate of roughly 3.5 centimeters each year, a distance so small that it seems almost an insult to mention it, and yet a distance that, multiplied across the 4.5 billion years since the moon's fiery birth, accounts for the vast gulf that now separates the two worlds. This drift is not random. It is not the result of chance or entropy alone. It is, instead, the direct and elegant consequence of the tidal relationship between Earth and Moon, a relationship in which the spinning Earth, rotating faster than the Moon orbits, drags its tidal bulges slightly ahead of the Moon's position, and in doing so, exerts a gentle gravitational tug that pulls the Moon forward in its orbit, adding to its energy, pushing it, ever so slowly, into a wider and more distant path around its parent world. And this same interaction, this same subtle exchange, works in the opposite direction upon the Earth itself, siphoning away some of the planet's rotational energy, slowing its spin, lengthening its days, a process so gradual that it operates on timescales of millions of years, and yet leaves its fingerprints everywhere, in the growth rings of ancient corals that recorded more days in their yearly cycles than our calendars now allow, in the fossilized rhythms of tidal sediments laid down long before there were eyes to witness them, in the quiet mathematics that tells us that a day on the early Earth, not so terribly long after the moon's formation, may have lasted only 6 hours, the planet spinning in a blur that would seem, to us now, almost frantic, almost feverish, a world spinning too quickly to properly hold its shape in the mind. And so we come to understand that the moon and the Earth are not simply neighbors sharing the same small corner of space, not simply two bodies that happen to orbit one another out of some cosmic convenience. They are, in the truest sense, partners in a single unfolding process, bound together by the same conservation of angular momentum that has governed every motion we have traced so far in this long meditation, from the collapse of the ancient nebula to the whirl of the galaxy overhead to the spin of the smallest particle within the smallest atom. The Earth gives, and the moon receives. The moon recedes, and the Earth slows. Neither can be understood in isolation, because neither exists in isolation, and this is perhaps the quiet lesson buried within all of this, a lesson that extends far beyond the mechanics of orbits and tides, a lesson about the nature of relationship itself, about how two things bound by an invisible force will inevitably, irrevocably, shape one another across the whole of their shared existence. Consider, then, what this means for the future, though future is a strange word to use when speaking of spans of time so vast that they exceed the entire history of life on Earth many times over. The moon will continue its slow retreat, centimeter by centimeter, year by year, and the Earth will continue to surrender its spin, day by day growing almost imperceptibly longer, until, billions of years from now, long after the sun itself has swollen into a red giant and reshaped the inner solar system beyond recognition, the Earth and Moon may finally settle into a state that physicists call tidal locking, a state in which the Earth's rotation slows to match the Moon's orbit exactly, so that one face of the Earth would show the Moon eternally suspended in the same patch of sky, unmoving, fixed, while the other face would never see it at all. It is a strange thing to imagine, a world divided by the presence and absence of its ancient companion, a world where half of humanity, if humanity still existed in any recognizable form, would gaze upward at a moon that never moved, and the other half would live beneath a sky forever empty of it. But this is a future so distant, so hedged about with uncertainties, that it exists more as a mathematical extrapolation than as a genuine prophecy, a glimpse into the kind of patient, almost geological time in which gravity does its work, indifferent to the brief and flickering span of any single observer who might wish to witness it. And yet, in this vast unfolding, in this slow dance stretched across billions of years, there is something that feels less like mechanism and more like meaning, though we must be careful, always, not to mistake the beauty of a pattern for evidence of intention behind it. The universe does not dance for an audience. It does not spin the Earth and pull the moon into its wide arc because it wishes to create something beautiful for us to contemplate in the quiet hours before sleep. And yet beauty is what remains. Beauty is what rises up out of these blind physical processes as surely and as inevitably as the tides themselves rise and fall along every shoreline on Earth. Perhaps this is the deepest truth hidden within the physics of spin, that meaning and mechanism are not opposites, that a universe governed entirely by the conservation of angular momentum can still produce, again and again, patterns that strike us as unbearably, achingly beautiful, patterns like the widening gyre of a spiral galaxy, like the tilted axis of a planet that gives us seasons, like the slow retreat of a moon that once hovered close enough to fill the whole sky. We began this meditation with spin as an abstraction, a curious fact about the universe that seemed almost incidental, a footnote to the more dramatic stories of stars and galaxies and black holes. But spin, we have come to see, is not incidental at all. It is woven into the very architecture of existence, present in the whirl of electrons around atomic nuclei, present in the rotation of planets and the orbits of moons, present in the majestic wheeling of galaxies through the cosmic dark, present even, some physicists suspect, in the fundamental geometry of spacetime itself, twisted and dragged into motion by the presence of rotating mass in a phenomenon so strange, so almost impossible to picture, that it deserves its own quiet unfolding, its own patient exploration, beginning perhaps with the strange behavior of light itself as it passes near a massive, spinning body, a phenomenon that carries us, at last, into the strange country of general relativity, where space and time themselves cease to be the fixed and passive backdrop we so often imagine them to be, and reveal themselves instead as something closer to a fabric, something that can bend, that can stretch, that can, in the presence of enough mass and enough motion, be dragged and twisted into new configurations entirely. This is the realm Einstein opened to us, though even Einstein, in his own quiet way, seemed almost reluctant to follow every implication of his own equations to their furthest conclusions. It was left to others, working in the decades after his great insight, to discover that a rotating mass does something profoundly strange to the space that surrounds it, something beyond the ordinary curvature that any mass, spinning or not, imposes on the geometry of spacetime. A spinning mass does not simply bend space. It drags space along with it, the way a spoon dragged slowly through honey pulls the surrounding fluid into a gentle, following swirl. This effect, known as frame dragging, or sometimes called the Lenz-Thirring effect after the physicists who first derived it, tells us that the very fabric of the universe near a rotating body is not still, is not static, but is instead caught up, however faintly, in the rotation of the mass that moves through it. Around the Earth, this effect exists, but so faintly, so imperceptibly, that it required decades of extraordinarily precise measurement to confirm it at all. Satellites carrying gyroscopes of exquisite sensitivity, spinning in orbit far above the planet's surface, drifted by mere fractions of an arcsecond each year, a drift too small for any of us to feel, too small to matter in any practical sense, and yet unmistakably present once the instruments were sensitive enough to detect it, a confirmation that the Earth, in its slow and stately rotation, drags the very fabric of space-time along with it in a whisper of motion that ripples outward into the surrounding cosmos. But if the effect around the Earth is a whisper, then the effect around certain other objects in the universe is something closer to a scream, a raw and violent distortion of space and time that pushes our intuitions past their breaking point. Consider the neutron star, that impossibly dense remnant left behind when a massive star exhausts its fuel and collapses in upon itself, compressing an entire sun's worth of mass into a sphere perhaps 20 kilometers across, a sphere so dense that a single teaspoon of its material would weigh, on Earth, more than a mountain. When such a star forms, it does not simply retain the modest rotation of its stellar progenitor. Because angular momentum must be conserved, because the universe does not permit spin to simply vanish when a star shrinks, the collapse causes the neutron star to spin faster, and faster, and faster still, In the same way, a figure skater accelerates by drawing her arms inward toward her body. Some neutron stars, known as pulsars, have been observed spinning hundreds of times each second, their surfaces moving at speeds that approach a meaningful fraction of the speed of light itself, their beams of radiation sweeping across the galaxy with the precision of a lighthouse built not by human hands but by the blind mathematics of gravitational collapse. Around such an object, frame dragging is no longer a subtle whisper detectable only through the most delicate of instruments. It becomes a defining feature of the surrounding space, a swirling vortex in the geometry of the universe itself, twisting the paths of anything that ventures near, bending the orbits of any lingering debris into strange and looping trajectories that no observer accustomed to the gentle mechanics of everyday life could easily predict. And if the neutron star is remarkable, then the black hole, that final and most extreme outcome of stellar collapse, pushes this phenomenon into territory that borders on the incomprehensible. A rotating black hole, the kind that astrophysicists believe is far more common in the universe than the simpler, non-rotating black holes once imagined in the earliest days of relativity, drags the fabric of spacetime around itself so powerfully that there exists, surrounding it, a region known as the ergosphere, a strange and turbulent zone in which nothing, not light, not matter, not even the empty vacuum of space itself, can remain still relative to the distant universe. Within the ergosphere, spacetime itself is forced into rotation, swept along in the black hole's relentless spin, so that any object entering this region, no matter what forces it might muster, no matter how powerful its engines or how determined its trajectory, will find itself pulled into a slow, inexorable orbit around the black hole's core, a captive not of gravity in the simple sense but of the twisting, dragging geometry of space itself. It is here, at the boundary of the ergosphere, that the ordinary language of force and motion begins to fail us entirely, and we are left instead with a strange and vertiginous realization that spin, at its most extreme, does not merely move through space, but reshapes it, remakes it, bends the very medium through which motion is even possible, until the distinction between the thing that spins and the space in which it spins begins to dissolve into something far stranger than our everyday intuitions were ever built to hold. And perhaps this is the point in our meditation where we must simply rest inside that strangeness rather than attempt to resolve it, because the ergosphere, and the frame dragging that produces it, are not puzzles awaiting a tidy solution so much as they are invitations, gentle and vast, to sit with the limits of our understanding the way one might sit at the edge of a dark lake at night, aware of depths that cannot be seen, content simply to feel their presence beneath the surface. The mathematics of general relativity can describe these regions with astonishing precision, can tell us exactly how far the ergosphere extends from a black hole of a given mass and spin, can predict, to remarkable accuracy, the strange looping paths that light itself would trace if it wandered too near. And yet even the physicists who work most closely with these equations will often admit, in quieter moments, that description is not quite the same thing as comprehension, that knowing the shape of a mystery is not the same as holding its meaning in the mind. There is, in fact, a peculiar consequence of a black hole's rotation that seems almost designed to humble any remaining confidence we might have in our intuitions about spin, and that is the theoretical possibility of extracting energy from the black hole itself simply by taking advantage of its rotation. This process, first described by the physicist Roger Penrose and now known as the Penrose process, suggests that an object entering the ergosphere, if it were to split into two pieces under just the right conditions, could send one piece falling into the black hole while the other piece emerges with more energy than the original object possessed before it ever arrived. The energy for this strange gain would come not from nothing, not from some violation of the universe's fundamental laws, but from the rotational energy of the black hole itself, siphoned away piece by piece, so that a black hole subjected to enough of these extractions would, over time, slow its spin, trading its rotation for the energy that escapes into the surrounding universe. It is a mechanism so exotic that it has never been observed directly, existing for now only within the realm of theoretical possibility, and yet it stands as a kind of proof, written in the language of mathematics rather than direct observation, that the spin of a black hole is not merely a descriptive detail, not merely a number attached to an otherwise simple object, but a genuine reservoir of energy, a vast and largely untapped well of motion that shapes the surrounding universe in ways we are only beginning to understand. And if we allow ourselves, for a moment, to zoom outward from this single exotic phenomenon, to lift our gaze from the extreme physics of black holes and neutron stars back toward the wider architecture of the cosmos, we find that spin, in all its forms, seems to occupy a peculiar and privileged place in the universe's own self-organization. It is there in the earliest moments after the Big Bang, encoded in the slight irregularities of the primordial plasma that would eventually collapse into the first generation of stars. It is there in the graceful spiral of galaxies, hundreds of billions of stars moving together in a slow, choreographed rotation that takes hundreds of millions of years to complete a single turn. It is there in the more modest spin of planets around their stars, in the tidal dance of moons around their planets, in the quiet rotation of atoms and the more frantic spin of subatomic particles, a property so fundamental that physicists consider it, alongside mass and charge, one of the defining characteristics of matter itself, present even in particles that possess no size at all, no physical extent that could, in any classical sense, actually be said to be spinning. This is perhaps the strangest revelation of all, more disorienting even than the ergosphere of a rotating black hole, this discovery that spin exists at the quantum level as a property utterly divorced from the everyday physical rotation we witness in planets and galaxies, a kind of intrinsic angular momentum that particles simply possess, as fundamental to their identity as their mass or their electric charge, unrelated to any actual spinning motion through space. An electron, as far as anyone has ever been able to determine, does not spin in the way a top spins or a planet spins. It has no measurable size, no surface that could be said to rotate, and yet it carries angular momentum as surely as if it were spinning, a quantum property so counterintuitive that physicists, lacking any better word, borrowed the language of the classical world and called it spin anyway, fully aware that the metaphor breaks down the moment you try to press it too closely, fully aware that this deepest layer of reality resists the very language we have built to describe it, and yet must be described somehow, must be given some name, some handle by which the human mind can grasp, however imperfectly, at a truth that operates entirely outside the realm of ordinary experience. And so we arrive, at last, near the end of this long and winding meditation, having traveled from the vast slow wheel of galaxies down to the strange and sizeless spin of the electron, having passed through the collapse of nebulae, the birth of stars, the violent creation of a moon out of planetary wreckage, the twisting of spacetime itself around the bodies that move through it. And what remains now in these quiet closing moments is not a conclusion in the traditional sense, not a tidy bow tied around everything that has come before, but something softer, something closer to a settling, the way a held breath finally releases, the way a long day finally gives way to rest. Because what we have traced, across all these separate scales and separate stories, is really only one story, told again and again in different registers, at different sizes, across different spans of time. It is the story of a universe that does not sit still, that cannot sit still, that seems constitutionally incapable of simple stasis, and instead expresses itself, at every level of its being, through rotation, through the patient turning of one thing around another, through the conservation of a quantity that most of us will go our entire lives without ever consciously naming, and yet which shapes nearly everything we experience, from the rising and setting of the sun to the changing of the seasons to the very fact that we stand, or lie, upon a solid world rather than drifting weightless through empty space. There is a kind of quiet comfort available here, if we allow ourselves to receive it, in recognizing that the same force which sends galaxies wheeling through the darkness also governs the gentle turning of the earth beneath us as we drift toward sleep, that the same conservation of angular momentum which shaped the aftermath of the Big Bang is, in this very moment, slowing the Earth's rotation by some infinitesimal fraction as the Moon continues its ancient, patient retreat. We are not separate from these processes. We are not observers standing outside the great turning wheel of the cosmos, watching from some safe and detached vantage point. We are, ourselves, spinning, carried along on the surface of a rotating planet that circles a rotating star that orbits within a rotating galaxy that moves, itself, through the vast and largely unmapped architecture of the universe, spin nested within spin, each one a small inheritance from the moment nearly 14 billion years ago when the first uneven scrap of matter began, for reasons we may never fully articulate, to turn. Perhaps this is why the subject rewards the kind of slow, unhurried attention we have tried to bring to it here, rather than the quick, urgent analysis more suited to a problem that needs solving. Spin is not a problem. It is a condition of existence, a texture woven into the fabric of everything that is, and to sit with it quietly, to let its implications settle rather than rushing toward some final and definitive answer, is perhaps the truest way to honor what it actually is. We do not need to resolve the mystery of why the universe spins in order to feel, in some deep and wordless way, the rightness of it, the sense that a universe without rotation would be a poorer, flatter, less alive kind of place, a universe of static points rather than dynamic relationships, a universe without the slow tidal conversations between planets and moons, without the majestic turning of galactic arms, without even the strange and beautiful spin of particles too small to ever be seen. And so, as this long night's meditation draws toward its close, there is only this left to offer: the quiet suggestion that the next time you find yourself lying still in the darkness, feeling perhaps entirely motionless, entirely at rest, you might remember that stillness, in this universe, is something of an illusion. Beneath you, the earth turns, carrying you eastward at hundreds of miles an hour even as you feel no motion at all. Above you, though hidden by daylight or clouds or simply the limits of unaided sight, the galaxy wheels slowly through its ancient rotation, indifferent to the small dramas of any single world. And within you, in every atom of every cell, the ancient silent spin of particles continues, unbroken, unceasing, a kind of motion so fundamental that it will likely continue long after you, and I, and everything we have ever known, have returned to the quiet dust from which we came.